Hello everyone. So this video begins the subject of optics. Before we begin, two announcements. First is make sure you watch the video on waves general properties. This is a continuation of that. And secondly, if you're finding these videos useful, please hit the subscribe and like button. Okay, so the first subtopic in optics is wavefronts and rays. So imagine a sunny day on a beach in Hawaii. You have all these lovely sand over here and you have these waves moving towards the beach. Being Hawaii, naturally you'll have a surfer or two on the water. Now let's say you're a proud parent of one of the surfers and you're dutifully video recording the surfer. Then what you notice is that you have a straight line motion. So although you have all this wave stuff going on, as far as you're concerned, the motion of this part of the wavefront is a single straight line. So that straight line, so if let's say this is the wave over here, so this part of the wavefront that's moving, the line that you draw over here, this thing is called a ray. The ray is perpendicular to the wavefront. It's in the direction of propagation of the wavefront, and usually it indicates the direction in which energy flows. There are rare exceptions, like certain kind of metamaterials, the energy actually flows backward to the phase velocity. So be that may, you can usually think of the ray as indicating the direction of propagation of the wave and the direction of flow of the energy as well. Now, a surfer is not the only way to visualize a ray. If you have a wavefront coming in, if you block portions of it, then on a foggy night, you can see the rays as you can see in this picture over here. So this is a picture I took a long time ago, and this QR code takes you to one of my collection on the internet and on the Flickr website. Now, when a wave crosses over from one medium to another, it has gone through an interface. And in the previous video, we saw the various things that can happen to a wave when it hits an interface. So here's a diagram of that. So first of all, the wave can bounce back. That's a reflection. And in this case, the angle at which it comes in equals the angle at which it leaves. This is the law of reflection. More on that later. Secondly, it can go through. That is the transmitted ray. For reasons that we'll see shortly again, this ray bends away from the normal or close to or toward the normal, depending on how the speed changes when it crosses the medium. And number three, some of the energy can simply get absorbed. It's neither reflected nor is it transmitted. So let's now look at this in a little bit more detail. So here's a quick demonstration of reflection. This is a little folding pocket mirror. I'm going to keep it here so that the surface is vertical. And here's a laser pointer. And it has a kind of broad beam. Let's look at this thing over here. You see how it's reflecting? The angle from on both sides is the same. If this is coming perpendicular, it bounces straight back. That's said to be normal incidence. So this is what the ray diagram looks like. The mirror that we had before, the shiny part, it was over here. You show the shiny part by not hashing the surface. You have this these hash marks over here. They're on the back side of the mirror to show that that's the rough side of the mirror. The one that's smooth, that's the shiny part. So the ray comes in from here, as you saw with the laser thing that I had before, and it bounces off the surface and it gets reflected. So this is called the incoming ray. This is the reflected ray. And the angle of incidence, the angle incidence is the incoming, it means incoming. So this thing over here, the angle is always taken between the ray and the normal, the perpendicular to the surface. So don't take the angle over here with the surface. The angle is with the normal. That's the angle of incidence. This is the angle of reflection, theta r. Again, is taken with the normal. And the law of reflection simply tells you that these two angles are equal. There's a way to actually derive and prove and explain this behavior. So technically it's not a law anymore, but for historical reason, we still refer to it as a law. So if you throw a ball against a wall, you'll notice that when it bounces off, those two angles are the same with respect to the normal. That's kind of what's going on. And next, let's look at the law of refraction. So when you have a ray in the air, for example, and it crosses over, it gets transmitted into glass, into a different medium, you'll find that not only is it transmitted, it gets bent. So unless the ray is coming along the normal at perpendicular to the glass, in which case it just goes straight through or gets reflected straight back. If it's at an angle, it has an angle on the other side. Just generally, it's different from the original angle. So why is that? So let's say you have a car going along a road and it's about to cross over into a surface which is different from the original one. This could be like gravel, it has more friction, it's going to slow down the car. If the car is coming at the normal incident, it'll just bounce right back, or it might slow down a little bit. If it's coming at an angle, look at what happens. This tire over here will slow down first because it's hitting the gravel before the right tire hits the gravel. So this is going to slow down, it's going to tend to bend. So this happens very often. Anytime a car like crosses a curb at an angle, it's going to tend to swerve and change the original direction. It's coming like this, it's going to bend around because it's slower over here. Or on the other hand, let's say it's on gravel and it's about to cross over into a smoother surface. If it's coming at an angle like this, then this tire will get a grip on this a good quality surface before the right tire. So it's going to speed up, and that's going to cause the car to turn away from the normal. So this is essentially the basis of refraction. Anytime a ray is coming towards crossing over into a different medium, if it's at 90 degrees, nothing's going to happen because the angle is 0 with respect to the normal. But if it's coming at an angle, it's going to get bent towards or away from the normal. So the change in the speed gives you the change in the angle. And when you work out the trigonometry, this is the relationship that you get. So if the speed in air, you take the ratio of the speed in air with respect to the speed of light in vacuum, is essentially the same. So in the case of air, this thing is just equal to 1 over here. It's the same speed as what you have in the case of vacuum. But when you go in glass, the speed is much lower. Often it's 2/3 of what it is in air or vacuum, the 300 million meters per second. So this ratio here of how fast light travels in vacuum, or which is almost the same as air, versus how fast light travels in that particular medium, that's called the refractive index. In the case of glass, this is in the neighborhood of 1.5. As I mentioned, the speed is 2/3 of what it is in the case of air or vacuum. So it's about 1.5. The exact number, of course, depends on what kind of glass it is, the different types of glasses. So this is the refractive index. And based on this change in the speed, you can calculate how much the angle will change. And that equation ends up being this thing over here. That's called the law of refraction. Sometimes it's called the Snell's law of refraction, but often simply the law of refraction. It tells you that the index of refraction in the first medium times sine of the angle, always relative to the normal in the first medium, that equals the same product in the second medium. So the second refractive index and the second angle over there. So n, remember, this is the refractive index. Is the ratio of the speed of light, the standard thing, 300 million meters per second, divided by the actual speed in that particular medium. That's the refractive index. So this is the relationship between these two, and that is the law. Sometimes instead of 1 and 2 for the first and the second medium, you might write it like this: I for incidence, the incoming ray, incident ray, and R for the refracted ray. Same with the angle over here. It doesn't matter which form you use. Oftentimes you'll have multiple media, 1, 2, 3, 4. And then rather than I and R, it's better to write the numbers 1, 2, 3, 4, and so on. So here's a little demonstration that shows you the refraction in an actual piece of glass. So this is an interesting demonstration that I found on YouTube. There's the YouTube address. You can go to that to look at the actual original video. But the point is that they send these light beams from air into glass. And now initially the rays are in the normal direction. So the angle is 0. Angle of incidence equals the angle of refraction. Both are 0. So it just goes straight through. So I've drawn the normal here. And in the second case, the rays are coming at an angle which is not along the normal. So notice over here, it's going into a denser medium. So a higher refractive index is referred to as a denser medium, optically denser medium. So it's going to a denser medium. So you have the car coming like that. This tire slows down first. It's going to swerve to the right-hand side. And you can see that here. So the blue is the extrapolated direction. And this white line over here, that's the actual light ray. It has bent in the direction of normal. So that's basically what happens. And this is the phenomenon of refraction. Now, I want to mention that when light is going into another medium that's perfectly transparent, like this slab of glass over here, even though the air and the glass are perfectly transparent, very clear and all of that, when light hits it, there is always a reflection as long as there's a change in speed. And that reflectance, the ratio of the intensities, that's given by this formula over here. You'll probably never use this, but I just wanted to mention this for completeness. Okay, so let's bring all this together by doing an example. And here's the example. A beam of light makes an angle of 28 degrees with a normal to a mirror made from a 2 millimeter thick glass, silver on the back. They give you the index of refraction of the glass. How far is the point at which the beam leaves the glass surface relative to the point where the beam enters the glass? Okay, so what's going on? You have a mirror made with glass. It's obviously not this thick, but anyway, this is what I have. And then the back of the glass is mirrored. So most mirrors that we see, you have a pane of glass, this silvering, something shiny coating on the back side over here. So the beam approaches the glass at an angle of 28 degrees with respect to the normal. You'll see when I draw the thing. It enters, it's going to get refracted, bent towards the normal. It then goes all the way down to the bottom over here. It gets reflected from the silvery coating, goes up, it gets refracted out again. So it enters at a certain point, goes in, reflected, and gets reflected and comes back out. The entry point and the exit point, there is a space between them. And that's the question. How much is the space between those 2 points? So when I draw this, what's going on may become a little bit clearer. So here's the mirror. That's the back surface. This is the top surface. This whole thing is glass. Okay. Then this is silvered on the back side. So you always show this with a rough hash coating over here. That shows that this is the rough surface. That's the shiny side, which is inside the glass. Now, the ray comes in at a certain angle to the normal. So that's the incoming ray. Here's the normal. Okay, so this is the normal. It's perpendicular. This angle over here that the incoming ray makes with the normal, let's call this theta 1. Now, this ray would have continued in this direction, but because of a refraction, it's going to bend toward the normal. So it ends up doing something like this. Okay, so that's the refracted ray. And then this angle here, let's call that theta 2. So this can also be called theta I for incident angle and theta R for refracted angle. But there's so many angles here, it's easier to just label them 1, 2, 3, 4. So that's that angle over here. Now, again, you have a normal at this point. So this is a normal. It gets reflected from here at an equal angle, the law of reflection. So it gets reflected like this. So this angle here on this side, this is also theta 2. This angle and this angle, they are equal because you have two parallel lines and a straight line going through. So these two angles are equal. Now this gets reflected. Here is the angle of reflection. This is theta 3. So theta 3 and theta 2, they are equal because this is a reflection, the law of reflection. So theta 2 equals theta 3 equals theta 2. Now the ray comes like this. At this point, again, there's a normal. Okay, so this is a normal. This would have gone in this direction, but now you're going from a dense medium. So here you have this is glass, so this is N2, this is air, that's N1. N1 is 1, N2 is 2. This is air, and this is glass. Okay, so you have these two media over here, something like this. So now you're going from glass into air. You're going from a optically denser medium. Oh, this is like not 2, it's 1.5. This is glass. Okay, so you're going from a dense medium into a rarer medium. So it bends. It's going to bend away from the normal. So instead of going this way, it's going to go in this direction. And this angle over here, let's call this thing theta 4. Okay, so these are the 4 angles. It comes in at a certain angle with respect to the normal. That's the incident angle. We call it theta 1. When it goes into the glass, it's going to bend toward the normal. So that angle is theta 2. Then it gets reflected here. So all of these angles, this angle, and that angle, those are all theta 2. Now once it does that, it comes over here. This is the normal. It makes an angle with respect to the normal over here. And these two angles are equal. So this is also theta 3 or theta 2. These are all of the angles. Then it comes to the second normal. It bends away from the normal. And you have this final angle over here, which is scribbled all the way down here. So this is theta 4. So make sure you understand everything that's going on. The ray comes in, refracts, reflects, refracts again. And the question is, what is the distance between the place where it enters and the place where it leaves? So what is that distance over there? So let's look at this triangle. Let's look at a magnified view of this triangle. So let's redraw this thing over here. Okay, so here you have something like this. Okay, it gets reflected in this manner. So these are the light rays. So let's look at this triangle over here. So this thing over here, from here to here, that's the thickness of the glass, and that's given in the statement of the problem. It's a 2 millimeter thick glass. So this is 2 millimeters. Okay, and then let's call this X. Then this distance is 2x. Okay, so this will have all of these triangles. They're similar triangles, and also the same dimension. They're identical triangles actually. So as a result, from here to here is half from here to here. This is the entry point of the light. That's the exit point of the light. So 2x. This is the whole question. What is 2x? That's what the question is asking for. The separation between the entry and the exit point. And if you can solve for x, you just take double that. That's going to be 2x. Now, look at this triangle over here. Let me slide this up a bit. Okay. So this is x. This is 2 millimeters. So the ratio of these two is equal to the tangent of this angle theta 2. So you have the following fact: the tangent of theta 2 is opposite over the adjacent. So that's equal to x over 2 millimeters. So let's call this equation 1. If we had a theta 2, you could put this in and get x, because you know the 2 millimeters. Then you take 2 times x, and that would be your final answer. But at this point, we don't know what theta 2 is. However, if you connect theta 2 with theta 1 over here, these are connected by the law of refraction through Snell's law. So you have the following connection between theta 1 and theta 2, which are a pair of refracted angles, and that connection is the following. So that's equation 1. You have n1 sine theta 1 is equal to n2 sine theta 2. And so we can we need theta 2, so we can solve for theta 2. So based on this, so this is the law of reflection. Okay, so that's the law of reflection. So from here you have a sine of theta 2 will equal n1 over n2 sine of theta 1, and n1 going up here, n1 is just air, the rays in the air. The refractive index of air and is the same as vacuum, is basically 1. It's slightly different from 1 actually. And then in here it's in the rays in the glass. The refractive index n2 of glass is 1.5. So put those numbers here. This is 1 and this is 1.5, and they gave you this incident angle. The first ray, it comes in at an angle of 28 degrees. So put it in. So this is 28 degrees. So now we can solve for theta 2. We'll crunch this out. So this is equal to, so find this final answer over here and then take the arc sine to get theta 2. This in any case is equal to, so it's equal to 0.313. And now you take the arc sine of theta 2 is that. So theta 2 is arc sine of 0.313. So you have theta 2 is equal to arc sine inverse of 0.313, and this is equal to 18.2. This is equal to 18.2 degrees. Let's call this equation 2. Now you can put this equation 2 into equation 1, and then from that you can solve for x. So let's do that next. So putting equation 2 into equation 1 gives you tan theta 2, which is now 18.2. This equals x over 2 millimeters. Rearrange this stuff and solve for x. X is going to equal 2 times tan of 18.2 degrees. And remember, x is only half of that width. So 2 times that x, that's 2 times 2 times tan of 18.2, you get 1.31 millimeters. And so here is what I was talking about. When you solve for x, that's only half of this total distance. This is where the light enters, that's where it leaves. So that's 2 times what you get from this triangle over here. Hence you have this extra factor of 2. The other 2 is the 2 millimeters, that's the thickness of the glass, and tan 18.2. So this gives you 1.31. And if you leave all of the distance in millimeters, you'll get the answers in millimeters, so there's no need to convert. But if in doubt, always convert things into standard units of meters. So that's here's an example of how you make use of the reflection and refraction laws. Next, we have the business of total internal reflection, often abbreviated as TIR. So imagine having two media with this interface in between. The light is going from a high refractive index medium such as glass into a low refractive index medium N2 such as air. In this case, if the ray approaches in this direction, instead of continuing straight, it's going to bend away from the normal. So it ends up doing something like this. If you increase this incidence, so this is the angle of incidence, okay, or theta 1. If you increase this angle here, if you come in like this, then this will bend even more. at some point this angle will be such that this can't bend anymore, and instead of doing that, it reflects back into the glass. Like so. When that happens, there's no more refraction. There's no more transmission of the light from the glass into the air. All of it gets reflected. Once it's reflected, the law of reflection applies. In that case, this angle is equal to this angle. You have a incident angle and a reflected angle. And this phenomenon is called total internal reflection. The light was not reflected because you had a shiny metal coating here, but it's attempting to go from a dense medium into a rare medium in which it bends away from the normal. It can bend only so far. Beyond that, it gets reflected back inside. And this is total internal reflection. So if you have a thin glass a pipe in which the light enters at an obtuse angle, a blunt angle, it's going to get reflected back and forth. And that's how optical fiber works. So what happens there is you have a little thin tube of glass, a little thread of glass like so, for example. And let's say light comes in like this. Notice the angle is very blunt, so it cannot get refracted. It gets reflected back in. And again, it's a very blunt angle, and it keeps getting reflected internally. And this is an application of TIR, of total internal reflection. This is a fiber optic, it's an optical fiber, and this is what carries a lot of our communication signals today. It's much more efficient than using copper wire and transmitting electrical signals. And then a bundle of these, if you have several of these things, and you stick this into someone's body, like that's what an endoscope basically is, then the light from every location on from the internal organs, you have light spreading out. That light will bounce around and come out. But the point is, when it comes out here, it's not mixed up. So the point originating at the light originating at every point over here will originate at a point at the other end of that particular glass fiber. So when you look at this over here, you basically see a map of the original stuff which was inside that person's stomach or whatever. And that's how an endoscope works. It's a bundle of optical fibers. So let's now take a look at some better quality diagrams of the same phenomenon. So here's the diagram we saw earlier. You're going from something like glass into air, a denser medium into a rarer medium, a higher index of refraction to lower. So then the ray bends away from the normal, as you can see here. Now if you keep increasing this angle, this will get bent more and more. At some point, it will emerge parallel to the surface. At that point, the incident angle is called the critical angle. If you go beyond the critical angle, it simply gets reflected. So this is the case when it's getting refracted. It is coming out from the other side. So here is the case where this angle is the critical angle theta c. In that case, the outgoing ray, the output ray, is parallel to the surface of the glass. If you increase this further, you have only reflection. And here it is. So if you increase this angle even a little bit more than the critical angle, then there's no possibility of refraction and transmission, and it gets completely reflected. And this is an extremely efficient reflection, much more than having a coating of silver or mercury or aluminum or something like that. And here is the thing that I talked about. So this is a light pipe, an optical fiber. The ray goes in at a sufficiently blunt angle. It's always more than critical, so it cannot emerge out. So none of it escapes. It just keeps reflecting back and forth, and out it comes from the other end. This is like as a child, you may have spoken into a pipe. Take a garden hose or some other pipe, you speak into it, and let your friend put it against their ear, and you can transmit a sound over long distances. It keeps it worming its way to the other end, and that's basically what happens here. And if you have a bundle of these fibers, and you stick them into the person's digestive system, etc., then this is what happened. At every point over here of that organ, you have light is being emitted. All of that is captured by each fiber, taken to the other end, and it emerges from this side with point-to-point correspondence. So when you look at the light emerging at those places, it's an image of what you have inside. And there is such an, that's a picture of such an image. And that's how an endoscope works. And here is this thing in operation in an actual situation. So you have this tube over here. That's the optical fiber bundle. As you can, you stick it in over here to the person's mouth and down the esophagus, etc. And then on this end, you look at the other end of the optical fiber bundle. You may use a small microscope or magnifier to look at it. But this person is very happily peering down that person's gut, basically. And so this is how the total internal reflection phenomena works and how it's used in practice.